can.
Now I'm
Okay. Welcome back to our Gong Show. And to get things started, we have Nico Cooper. He'll tell us about holographic equidistribution.
Thank you. Yeah, so sorry guys, it's not Fortuitous Friday, it's Average Friday. I'm going to tell you guys about holographic equidistribution. This phrase haven't really come up with this, but good news is I don't have to explain holography, I just have to explain equidistribution, and I think I can manage to do that in 5 minutes. This is mostly going to be an ADS3 CFT2 type of talk. It's based on my paper that came out, I was going to say earlier this month, but around a month ago. Yeah, and my advisor is Al Shapir, but this is related to the Narayan CFT, code CFT type of stuff, but goes a little bit beyond as well. So we're going to be concerned with these things called Hecky operators. They show up in 2D CFT in a bunch of different contexts. I'm mainly going to focus on a couple of examples. Well, for that I should tell you a little bit about how they act. I'm not going to write it down explicitly, but here's what we care about. It takes a modular invariant function and maps it to another modular invariant function. So as you could probably guess, they show up in contexts where, say, I'm taking something that looks like a CFT partition function and generating a new CFT. I might have an example in mind that you'll see. So first one where they show up is averaging over Narayan CFTs, but in particular the ones that are classified by error correcting codes. That's my advisor's program. And the main punchline there is that we have this continuous average that you can define over CFTs, and this is a well-defined discrete subset. And the average over ZP cross ZP codes takes this very simple TP Hecky operator form over some vacuum character. And then a second example where they show up is in symmetric product orbifolds as well as cyclic product orbifolds, where I take n copies of any CFT I want, and then I gauge some permutation symmetry. And here we're already seeing something that we just learned a bit about. We're seeing a lot of erratic n dependence in the sense that the Sn symmetric product orbifold depends on all these different Hecky terms that depend on partitions of n and things like that. But we have the following theorem that we can use, which is that in the large n limit, which is what we're caring about for both, first example, n equals p, a prime, we have this theorem that only my advisor and Anatoly Damarsky and Ofer Aharoni have used in their paper from 2022. I forgot to put it there. This Hecky equidistribution theorem from around 2001, which says that in the large n limit for just some term that's some Tn, some Hecky operator acting on a partition function, the big part is that part of the partition function integrates away in the sense that the Hecky operator sort of looks like it's converging to an integral. But it only converges to an integral for the square integral part of the partition function. This was the sort of split that I was annoying Hong about earlier, that there's a part of the partition function that in the large n limit sort of averages away, and then there's a part left over that in the process you have to modular complete, and our natural way of doing this is conducting a Poincare series. So the biggest punchline here is wherever you've got Hecky operators showing up and taking a large n limit, then you've got this statement that all you're left with is a Hecky operator acting on some Poincare series. If you ever heard the phrase before, these Poincare series are what show up in ADS3 holography. This is the sum over handle body geometries in the bulk. Okay, kind of a lot, but this was the main punchline, and funny thing is, first example has to do with averaging, second a priori doesn't at all. And there are other examples where Hecky operators show up, and you can make the same sort of statement. Okay, so I think in my last minute or so, right, so that's what I was just saying, you get a whole sector integrated out. Another way of saying this for symmetric product orbifolds in particular is that at some point in the large n limit in your partition function, n is going to infinity, so you would have an infinite amount of terms, but they get truncated off somewhere. Okay. So a little bit of some tentative interpretation for this. It turns out that this Hecky equidistribution theorem, that all of the images of the Hecky operator are converging to an integral, so that sort of sounds like what it's called, equidistribution. This happens to be implied by what's called horocycle uniform distribution. Horocycles are curves in the upper half plane that are perpendicular to geodesics. And it happens to be that There's a result for uniform distribution of Hora cycles in the fundamental domain of SL2Z, and this implies Hecke equidistribution. And there was a recent proposal that you can do a bulk cutoff on Hora cycles, and that gives you regulator-independent answers, so these might have something to do with each other. Thank you. Questions, comments, concerns?
Question? All right, thank you.
Thank you, guys.
Hello all. So I'm going to talk about one of our upcoming work with Jim, Yipang, and former students Ida and Robert. It's well known that pure and equal to 2 supergravity for derivative level is unique in 5 dimensions. So one could ask whether we can make a similar statement when we couple these two vector multiplets. So just a quick background. So n equal to 2 supergravity coupled to vectors is something that naturally arises in the Calabi-Yau compactifications of M theory. And it's usually written in terms of these constrained scalars. And the 2 derivative action, the bosonic sector of the 2 derivative action can be written in terms of these very special geometries. So one of the models that we are interested in is going to be the STU model, for which we have 2 vectors, and of course the graviphoton, and another simpler one which we will call the C112 model, for which we only have like 1 vector. So there are different ways of constructing for derivative completions to this. So from a bottom-up point of view, one could use the machinery of superconformal tensor calculus. An example of this is to start from a superconformal multiplet. For example, here the standard while multiplet, couple it to some vectors, n vectors, and use a linear multiplet as a compensator to reduce it to Poincare supergravity. And it turns out that in the ungauged limit, this construction only admits 1 non-trivial invariant at 4 derivative level, the so-called Weil-squared invariant, which schematically takes a form like this. So another example is to look at what's called the Diletton-Weil multiplet that admits 2 non-trivial invariants. We could also look at some top-down construction, which usually involves some sort of dimensional reduction. For example, one could reduce 10D heterotic string on T5 and truncate it to the n equal to 2 sector, which gives a invariant that roughly schematically looks like this. We could also look at some 6D theories where it's known that the n equal to 1, 0 theory has 2 non-trivial independent gravity invariants, reduce it to 5D, and compare all these things. Now, obviously, there's going to be a lot of field redefinition freedom between these, and one would expect that if we go to a minimal field redefinition frame, many of them will agree with each other. And it turns out that it happens to be not the case, and the invariants that have gravity happens to differ from each other in terms of vector-only terms that look like this. So for example, if I take the heterotic case, which has 2 vectors and a graviphoton, and compare it with the standard while for appropriate process of this lambda, they differ by sum of 2 terms, which are exactly of this form. So with appropriate overall factors. So one would expect to have some vector-only invariants that can be constructed for n equal to 2 theories in 5 dimensions. So we could ask a much more general question. So can we go to a rigid limit where we can turn off this gravity and extract just these vector multiplets, vector invariants? We can. So if we take this limit of this, for example, here I'm doing it for this standard while invariant. It turns out that we can separate it into this gravity-only piece, vector-only piece, and a gravity-vector coupled piece. And the vector invariant happens to take a schematic form that looks like this. So this is like a symmetric object, and this is like a pairwise symmetric object. And this curly F is like schematically some superfields, vector superfields. And we can compute these objects explicitly for simple models like the STU model and C112 model. And we could conjecture that, for example, for the STU model, we could construct 2 independent vector invariants, which is of this form. So we also looked at static BPS black hole solutions to all these models. And it turns out that, surprisingly, if the for derivative completion differ only by these kind of vector invariants, they share the same kind of BPS solution. So vector invariants are not going to cause any further corrections to the BPS solutions. And hence, like all the thermodynamic properties is going to remain the same. For example, the Wald entropy for any for derivative corrections to the ST model that involves gravity takes the usual form. And I will stop there, I guess.
Question? All right, thanks.
David, just a curiosity, did you also study the case with the cosmological constant, where you add the cosmological constant?
No, this is the ungaged limit, so we did not study anything with the
You
cosmological
didn't look at
constant.
that.
Yeah.
All right, thanks.
All right, thanks. So my name is Daniel Wang, and today I'm going to talk about this thing called a random matrix statistic of a BCFT ensemble. And this is based on work with Daniel Jeffers, Lisa Rosenberg, and Deb Saka. So, so to give a quick review, I guess it has been mentioned in this conference that called a Jensen wormhole, or the wormhole that has the topology of a cylinder times a circle, computes the leading spectral density correlation of a CFT, a 2D CFT. And this rho correlator at genus 0 is exactly given by the universal expression that also describes the correlation in the JT matrix model and all other random matrix statistics. So that suggests that in general, this matrix model also may predict all these gravity partition functions on more general topologies, not just the one that's just a torus times the interval. For example, it's proposed that if you look at the correlation of the matrix model with n spectral densities at genus G contribution, then the expectation is that it would be computing, or it should be due to the partition function of 3D gravity on Riemann surface across S1. However, this has been so far an open question to prove in general, and it's a difficult question. And the situation is very similar in fermionic gravity, which Joaquin talked about yesterday, because it's already pretty hard at when you have 2 boundaries, and then when you have more boundaries and higher genus, this computation becomes very difficult. So to make progress, we look at a simpler question, which we call the open sector of the spectrum. So the open sector here means you should think about the CFT as, this is just a language, as sort of a string worksheet. So the closed sector corresponds to bulk operator insertions, which then correspond to closed strings. But then you could also have CFTs living on the boundaries. That's why we call these BCFTs. And then there are boundary operator insertions, which are related to open strings. So the closed strings are slightly more difficult because they have both the energy and the spin. Here, the main simplification comes from the fact that these open strings in the 2D CFT only have energy, so there's no spin dependence. So these correlators now look like a rho E1, etc., to rho En, and then the genus G compute. And then the proposal is that the open sector is now described by a single matrix model. There's no spin dependence, so there's no need for RMT2, for example. And then the reason why we look at these particular, and then the proposal is that they're related to gravity on sigma Gn cross an interval. The reason why these are the relevant manifolds, I guess one of the reasons is that each of these manifolds has n annular asymptotic boundaries. And we're interested in annular partition functions because if you look at the open string, take the trace over the Hilbert space, that gives you the annulus. So if you compute n correlations, then that would correspond to a manifold with n such boundaries. Yeah, so that's the expression, trace over the Hilbert space. So the main result here is that for sigma 02, genus 0, 2 boundaries, that's the analog of the torus wormhole or the Kohler-Jensen wormhole. We have to do an explicit path integral. So it's very similar to what they did, but for the open case. It turns out that for Riemann surfaces with a negative Euler characteristic, you don't have to do the path integral explicitly, because there is sort of a trick using Versal T to compute the path integral as an inner product. Although that's not exactly the right answer because gravity differs from Versal T, in particular on these off-shell manifolds by large diffeomorphisms. So you have to gauge those large diffeomorphisms explicitly, but then once you've done that, you get exactly the right answer. So finally, the conclusion is that 3D gravity on these manifolds is precisely described by a single random matrix theory, and namely a very thorough minimal string. That's all I want to say. Thank you.
How is the left-hand side of equation 3 defined? So if you are doing like JT gravity, then the G contribution is like, okay, you're expanding the e to ds naught even in the random matrix,
Right.
etc. But here, yeah, what does the sub G of the ensemble means that would single out some subset of the geometries as opposed to other geometries with the same boundaries but that don't split into sigma times an interval?
Right. I guess here there are other manifolds that would seem to correspond to even more complicated descriptions on the boundary side. For example, you might expect the tensors that involve OP coefficients. Here, this particular class of manifolds, I mean, you could think of it as first a guess, but then somehow when you actually check it, it's precisely these manifolds that contribute to that correspond to the precise expressions. But also to answer your question, the left-hand side is defined to be the genus G contribution to the matrix model in a large n expansion. So it's not a bulk computation. The right-hand side is a bulk expression. The left-hand side is the large n expression from the matrix model. And G there, you don't have to call it genus, but it's sort of defined to be like what's the smallest genus of the 2D surface where you can put this diagrammatics on without self-crossing for these matrices. Yeah.
Good, all right, thank you.
Yeah, thank you.
Okay, my name is Jingchao Zhang. I'm going to talk about a theorem tells us the universality of the 3/2 log T correction to extremal black hole entropy. This is based on a recent work. Okay, this is not the latest version of my slides, but it's okay. A recent work like several weeks ago with Leo. Okay, so it is well known that for extremal black hole, the near horizon part develop ADS2 throat. If you do a Euclidean path integral in this ADS2 region, you find there exists a set of tensor zero modes. That is telling us if we calculate the one loop determinant, you got 1/0. It is a signal that indicating that when you take the t goes to 0 limit, before you really see the extremal black hole, it is already, there's large quantum fluctuations spoil down the semi-classical picture. So this, in a two-dimensional perspective, these fluctuations are controlled by Schwarzian action. You can do the calculation of the Schwarzian theory, got the correct partition function, also the correction to the entropy. But you can also directly do this calculation in high dimension, especially for actually symmetric case, like we don't know how to do the dimensional reduction properly. So we apply this in our last paper 2 years ago. We apply this higher dimensional calculation to many different examples, different black holes. This gives us a lot of experience and inspire us to develop this into a theorem. So this is the main result. We would show a theorem that proves the universality. Our setup is a gravitational theory in d greater or equal to 4. For the matter sector, we have any number of uncharged scalar abelian gauge field, and the scalar can have arbitrary scalar potential. So it can include cosmological constant. And we consider the actually symmetric case, so the black hole can rotate. So we prove. We show that the near horizon region always have the ADS2 structure. There always exists a set of tensor zero modes. And by some calculation, we show that the lifted eigenvalue after some proper regularization of the zero modes, the lifted eigenvalue also always have some pattern. And it leads to the 3½ log T correction. Okay, so we start from the near horizon region. This is the near horizon metric with the help of a lemma proved by Konduri, Luciti, and Rao. We do a little bit extension. This is the near horizon metric. Always have the ADS2 part. All the information about the original black hole is included in the G1, GMM, GIG functions. And we prove another lemma tells us there always exists this set of tensor zero modes. This G1 is same G1 as above. These tensor zero modes are higher dimensional avatars of the Schwarzian boundary reparameterization modes. And actually in this paper, we provide a one-to-one map. You can show that actually this index n here is actually the same n you use for the Fourier modes on the boundary reparameterization. Okay, so in order to calculate the one-loop determinant, we need to regularize the zero modes by a small but non-zero temperature configuration. By doing all these different black holes, we impose an empirical or structural ansatz for this small fluctuation. Also for the matter fields. But it turns out the matter fields are not super important because we proved another lemma that in the linear Ulrich operator, even though there's many terms, most of them cancels out. The matter information of the matter sector does not enter into the lifted eigenvalue. So we only need the metric. And by brute force calculation, we got the lifted eigenvalue, and it always shows the pattern of proportional to NT. After zeta function regularization, you got the 3½ log T correction to the entropy. So this wraps up the proof. Don't worry, the other two slides is just in case you are curious about how the empirical ansatz looks like. Yeah. So I want to emphasize that the matter choice is not special. We expect this works for any other type of matter. Thank you.
Question?
Just like in the Konduri, Luciti, and Real ADS2, is there any way to show if there is a universal order T? Is the order T correction also universal to some extent? Like even recursion 1, the delta T?
This is like a zeroth order metric, and the order T thing is our empirical assumption. And we can check this assumption, this thing, applies to all the examples we have, but it is constructual.
Okay, but do you think if it could be, one could use similar techniques to prove that you can solve the Einstein equation to order T and that this is universal?
In principle, yes, but I would assume this is much harder than the zeroth order. Yeah.
All right.